Hello, and welcome to the town that slept forever. I'm so glad you found your way here. Whether you're curled up after a long day, your mind is still buzzing from the day's events, or you simply find comfort in drifting off to the gentle rhythms of the universe. This is a space made for wonder, for quiet contemplation, and for the soft glow of curiosity. Tonight, we're going on a journey, a slow, meandering stroll through one of the most fundamental and beautiful truths of our cosmos. We're going to ask a question that seems simple but leads us to the very heart of reality. Why does light, of all things, have a speed limit? But before we begin our journey, I'd love to know, where are you listening from right now? Are you in a bustling city where the lights never truly fade, or in a quiet countryside where the stars still own the night? What time is it for you? Are you sipping a warm drink, wrapped in a blanket, with the day's worries slowly melting away? If these sleepy explorations bring you peace, I'd be deeply grateful if you gave this video a like and tapped that subscribe button. It helps other weary travelers and curious minds find their way to this quiet corner of science, and it allows me to keep crafting these starlit journeys for you. Now, a gentle warning. I do hope this isn't too interesting. The goal here is rest. But if you find yourself still awake at the end, well, at least you'll carry with you a deeper understanding of the universe's inner workings. That's not such a bad trade, is it? So, find a comfortable position. Let your breathing slow. Close your eyes if you like. And let's begin our slow, thoughtful wander through the story of light and why it seems to be in such a constant, unwavering hurry. We all think we know light. You flip a switch and a room is illuminated. The sun rises and the world is bathed in gold. It lets you see your cat's judgy expression and makes your phone screen glow in the dark long after you promised yourself you'd go to sleep. But what is it, truly? Is it a wave? Particle? A cosmic courier with an impossibly strict delivery schedule? The short, wonderfully strange answer is yes. It's all of those things. To understand why it has a speed limit, we first need to understand what it is that's doing the speeding. Let's start with the fundamental unit of light, the photon. Imagine them not as tiny balls, but as massless packets of pure energy, little messengers zipping through the void at the fastest speed the universe allows. But these are no ordinary messengers. They defy our everyday intuition. Unlike a marble or a grain of sand, a photon has no mass. It has no rest state. From the moment it is born, emitted from a star, a light bulb, or a firefly, it is moving at the speed of light. It never accelerates, and it never decelerates until it is absorbed, delivering its energy and ceasing to exist. It's a burst of pure existence in motion. Now, here's where it gets beautifully complex. Photons are also waves, but these aren't waves like water or sound. They are ripples in the very fabric of reality itself, electromagnetic waves. Picture this: an electric field and a magnetic field, locked in a perfect, self-sustaining dance. As the electric field oscillates, it creates a changing magnetic field. That changing magnetic field, in turn, creates a changing electric field. They push and pull each other forward through empty space, vibrating at right angles to each other and to their direction of travel. It's a self-propelling cosmic dance that requires no floor, no air, no medium at all. This is a crucial point. Sound needs air to travel. Water waves need water. But light, in its purest form, needs nothing. It travels through the perfect vacuum of space utterly unhindered. That's why we can see the sun, a ball of fire 93 million miles away. Its light has crossed that vast, empty expanse without a single atom to carry it, without a single rest stop. The light we see, the red of a rose, the blue of the sky, is just a tiny sliver of a much grander picture. Imagine a piano keyboard that stretches for miles, with keys representing every possible wavelength of light. The visible spectrum, the colors of the rainbow, is just a single octave in the middle of this immense instrument. On the far left, with long, lazy wavelengths, we have radio waves. They can be miles long and carry music, news, and data through our atmosphere. Next are microwaves, which heat our food and let our phones communicate. Then comes infrared, the warmth you feel from the sun or your radiator, the secret language of your TV remote. In the middle are little visible octave: red, orange, yellow, green, blue, indigo, violet. Beyond violet, the wavelengths get shorter and more energetic. Ultraviolet light from the sun gives us vitamin D, but also sunburns. X-rays have so much energy they can pass through soft tissue, allowing us to see our bones. And at the far right of the cosmic piano, we find gamma rays, ultra-short, high-energy spikes born in the furnaces of exploding stars and nuclear reactions, capable of piercing through almost anything. The breathtaking thing is this: despite their wild differences in energy and application, all of these, from the longest radio wave to the most energetic gamma ray, are fundamentally the same phenomenon. They are all electromagnetic radiation. And in a vacuum, they all travel at exactly the same unwavering speed, 299,792,458 meters per second. That number, 299,792,458, is so immense it feels abstract, almost nonsensical. To put it in bedtime terms, if light were a runner, it could lap the entire Earth more than 7 times in a single second. Not bad for something with no legs, no engine, and no fuel. But light isn't always in a vacuum. When it passes through a medium like water, glass, or even diamond, it slows down. This isn't because it's getting tired. It's because the photons are interacting with the atoms in the material, being absorbed and re-emitted in a complex subatomic dance. It's like trying to walk in a straight line through a crowded, bustling party. You're still headed in the same direction, but you're constantly bumping, weaving, and pausing, making your overall progress slower. This slowing down is what causes refraction, the bending of light. It's why a straw looks bent in a glass of water and why a diamond, expertly cut, can trap light inside, bouncing it around to create that brilliant, fiery sparkle. The light is taking a more scenic, complicated route. When we see a rainbow, a prism, or the iridescent sheen of an oil slick, we are witnessing light being sorted by its wavelength. Each color corresponds to a different wavelength. Red light has long, stretched-out waves. Violet has short, rapid-fire waves. But they are all photons, all electromagnetic waves, just vibrating at different frequencies. Your eyes are exquisite instruments tuned to this specific range. Specialized cells called cones are sensitive to red, green, and blue wavelengths. Your brain mixes these signals to create the entire palette of color you perceive. So, an apple isn't inherently red. It absorbs most wavelengths of light but reflects the specific wavelengths we have learned to call red. Color, then, is not a property of the object itself but a story, an interpretation crafted by your brain from the vibrations that happen to reach your eyes. And as if all this weren't strange enough, let's return to that idea of masslessness. Because a photon has no rest mass, it doesn't need energy to keep moving. It must move. It has no other state of being. If a photon could stop, it wouldn't just be pausing. It would simply cease to exist. For light, it's motion or nothing. All are gone. So, let's hold this image in our minds as we drift deeper. Light is a restless, massless traveler, both a wave and a particle, carrying energy across the universe at a speed that is both immense and unchangeable. It shows us the faces of those we love, the words in our books, the glow of the stars. And it does all this while obeying a rule so fundamental that it shapes the very nature of reality. Let's take a gentle step back in time. Long before lasers and atomic clocks, before we could even conceive of measuring something so impossibly fast, humans looked at light and saw instantaneity. You lit a candle, and the room was illuminated. The sun rose, and the world was golden. There was no delay, no travel time. It seemed obvious that light moved infinitely fast. Even the ancient Greek philosopher Empedocles, who suggested light had a finite speed, was largely ignored. Aristotle, whose word was law for centuries, declared light instantaneous, and that, it seemed, was that. Curiosity was shelved. Then came Galileo Galilei, a man not known for taking because Aristotle said so for an answer. He was the kind of person who would drop cannonballs from towers and point telescopes at the heavens to see for himself. Around 1638, he devised what might be the most charmingly optimistic experiment in the history of science. His idea was simple. He and an assistant each took a covered lantern and stood on hilltops about a mile apart. Galileo would uncover his lantern. The moment his assistant saw the light, he would uncover his own. Galileo would then try to measure the time between sending his signal and seeing the return flash. It was a beautiful idea, but doomed from the start. Human reaction time is agonizingly slow in the realm of light. It takes about a quarter of a second to react to something you see. Light, meanwhile, covers a mile in about 5 microseconds, a tiny fraction of that time. It was like trying to time a bullet with a sundial. Unsurprisingly, Galileo concluded that if light did have a speed, it was 10 times faster than sound, and far too swift for him to measure. He hadn't found the answer, but he had asked the right question, and that was a monumental step. The first real breakthrough came not from a terrestrial experiment, but from looking skyward. In 1676, Danish astronomer Ole Romer was meticulously observing Io, one of Jupiter's many moons. Io orbits Jupiter with the regularity of a perfect clock, disappearing behind the gas giant, eclipsing, and reappearing at precise intervals. But Romer noticed something peculiar. The timing of these eclipses wasn't perfectly consistent. When Earth was farther away from Jupiter in its orbit, Io seemed to appear later than expected. When Earth was closer, the eclipses happened earlier. Romer had a brilliant insight. What if the moon itself was perfectly punctual, but the light bringing us the news of its arrival was not? The delay, he reasoned, was the extra time it took for light to travel the additional distance across Earth's orbit. He estimated that light took about 22 minutes to cross the diameter of Earth's orbit. Using the best estimates for that distance available at the time, he produced a rough calculation for the speed of light. It wasn't perfectly accurate, but it was revolutionary. He had proven for the first time that light had a finite speed. Took time, not much, but enough to matter. The baton then passed to a French physicist, Hippolyte Fizeau, who in 1849 devised the first truly successful terrestrial measurement. His setup was clever and mechanical. He shone a bright beam of light at a mirror several miles away. But in the path of the beam, he placed a rapidly spinning toothed wheel. The light would pass through a gap between the teeth, travel to the distant mirror, bounce back, and, if the wheel hadn't moved too much, pass back through the same gap to be seen by an observer. But if the wheel was spun just right, the returning light would find that the gap had been replaced by a tooth, blocking the light. By knowing the distance to the mirror, the number of teeth on the wheel, and the rotational speed at which the light was extinguished, Fizeau could calculate the time it took for the light to make its round trip. His result was astonishingly good, 315,000 kilometers per second, only about 5% off the modern value. He had captured light in a race against a machine. Soon after, Léon Foucault, of pendulum fame, refined the method. He replaced Fizeau's toothed wheel with a rapidly rotating mirror. As the mirror spun, a beam of light would bounce off it, travel to a stationary mirror, and return. In the tiny time it took for the light to travel, the rotating mirror would have turned a minuscule amount, deflecting the returning beam to a slightly different spot. By measuring this deflection and knowing the speed of the mirror's rotation, Foucault could calculate the speed of light with even greater precision. His method was so good he was able to prove that light traveled slower in water than in air, a critical clue to its wave nature. The most iconic figure in this chase was Albert A. Michelson. In the late 19th century, he took Foucault's rotating mirror method and perfected it with breathtaking precision. In his most famous experiment, he used an elaborate setup of mirrors in a long, evacuated tube to avoid the distorting effects of air. His measurements were so accurate that they stood as the gold standard for decades. His lifelong dedication to measuring light earned him the Nobel Prize in Physics in 1907, the first American to receive the honor. Not a bad reward for someone who spent his life chasing beams of light with mirrors. Today, our tools are even more incredible. Lasers, atomic clocks, and global satellite networks. But the most profound shift happened in 1983. We became so confident in the constancy of light speed that we flipped the equation entirely. We no longer measure the speed of light. We use the speed of light to measure everything else. The meter is now officially defined as the distance light travels in a vacuum in 1/299, 792, 458 of a second. The speed of light is no longer a measurement. It is a definition, a constant that underpins our entire system of measurement. It all started with people on hilltops with lanterns, watching moons of Jupiter, and spinning wheels, wondering if the universe might be a little slower than it looks. And in that story of curiosity and persistence, there is a quiet, profound beauty. So now we come to the heart of our sleepy inquiry. We know light has a speed and we know how we measured it. But why this number? Why 299,792,458 meters per second? Why not a nice, round 300 million or 500 million or simply infinite? Why does this ethereal, massless energy have to obey a cosmic speed limit? The answer takes us on a calming stroll into the most elegant and mind-bending part of physics, guided by two brilliant minds. In the 1860s, a Scottish physicist named James Clerk Maxwell performed what can only be described as scientific magic. He took all the known laws of electricity, from figures like Benjamin Franklin, and magnetism, from pioneers like Michael Faraday, and distilled them into four concise, beautiful mathematical equations. These are now known somewhat dryly as Maxwell's equations. You don't need to understand the math, but you should appreciate their power. They describe how electric fields are created by charges, how magnetic fields are created by currents and changing electric fields, and how the two fields dance together. When Maxwell played with these equations, he discovered something that must have made his heart race. The equations predicted that a changing electric field would create a changing magnetic field, which would create a changing electric field, and so on, a self-perpetuating wave that could travel through empty space. And when he calculated the speed at which this electromagnetic wave would have to travel, based on the fundamental constants of electricity and magnetism, he arrived at a number 299,792,458 meters per second. He was stunned. This number, emerging purely from theory, matched the best experimental measurements for the speed of light. The conclusion was inescapable. Light is an electromagnetic wave. Its speed wasn't arbitrary. It was a fundamental property of the universe, baked into the very fabric of electromagnetism. Light speed is the only speed an electromagnetic wave can have in a vacuum. Anything else would break the universe's rules. But this only answered part of the question. It told us what the speed was, but not why it was a limit. For that, we need a young patent clerk named Albert Einstein. In 1905, Einstein published his special theory of relativity, and with it, he rewrote the rules of reality. At its heart was a single, deceptively simple postulate. The speed of light in a vacuum is constant for all observers, regardless of their own state of motion. This sounds tame, but it is utterly revolutionary. Imagine you're on a spaceship moving at 99% of the speed of light. You turn on a flashlight. Common sense says that someone standing on a planet watching you fly by would see your flashlight beam moving at your spaceship speed plus the speed of light. But they don't. Both you, inside the ship, and the observer on the planet We'll measure the beam's speed as exactly 299,792,458 meters per second. Not a fraction more, not a flicker less. To make this possible, reality itself has to bend. Einstein discovered that to keep the speed of light constant for everyone, space and time must be flexible. Time dilation. The faster you move through space, the slower your clock ticks relative to someone at rest. This isn't a mechanical error. It's a fundamental property of time. We've tested this with particles called muons, which decay quickly at rest, but live much longer when hurled at near-light speeds in particle accelerators. Their internal clocks literally slow down. Length contraction. As you approach light speed, distances in the direction of your travel appear to shorten. Your spaceship would physically get shorter from the perspective of a stationary observer. Relativity of simultaneity. Two events that appear to happen at the same time for one person may not be simultaneous for another if they are moving relative to each other. There is no universal now. So why can't you go faster? As you accelerate an object, its mass, in a sense, increases. Not because it's getting heavier like a rock, but because it requires more and more energy to push it just a little bit faster. As you approach the speed of light, the energy required to continue accelerating approaches infinity. Since there is no infinite energy source in the universe, nothing with mass can ever reach, let alone exceed, the speed of light. The speed of light, therefore, isn't just the speed of light. It is the cosmic speed limit, the maximum speed at which any information, energy, or causation can travel through the universe. It's a barrier woven into space-time itself. And perhaps this is the most soothing thought of all. This cosmic speed limit is what protects our sense of reality. It ensures that cause always comes before effect. You cannot see an event before it happens. You cannot send a message into your own past and create a paradox where you prevent yourself from sending the message. The universe, with this simple, constant speed, prevents chaos and maintains a logical, orderly flow of time. It's a safety rail on the edge of possibility, keeping everything understandable and calm. This constant, c, is more than just a number on a chalkboard. It's the silent, invisible architect of our daily lives and our cosmic perspective. Every time you send a text, stream a video, or listen to this audio, you're relying on light speed. Our global internet is built on fiber optic cables, slender strands of glass that carry pulses of light. The information in your cat video is encoded in these flashes, racing across continents and under oceans at nearly 300,000 kilometers per second. The slight delay in a video call with someone on the other side of the planet, that's the time it takes for light to make that journey. The universe is imposing a tiny, necessary pause for connection. Your GPS is a testament to Einstein's genius. The satellites that pinpoint your location are moving very fast relative to you and are in a slightly weaker part of Earth's gravitational field. According to special relativity, their high speed makes their onboard atomic clocks tick slower. According to general relativity, the weaker gravity makes them tick faster. The net effect is that they gain about 38 microseconds per day. Without correcting for this, your GPS would be wrong by over 6 miles per day, rendering it useless. Your navigation to the nearest coffee shop depends entirely on our understanding of light's constant speed and the relativity it implies. When you look at the night sky, you are a time traveler. The light from the nearest star, Proxima Centauri, is over 4 years old. You are seeing it not as it is, but as it was 4 years ago. The light from the Andromeda Galaxy is 2.5 million years old, arriving from a time when early humans were just beginning to walk the Earth. The Hubble and James Webb Space Telescopes see galaxies whose light has been traveling for over 13 billion years, from a time when the universe was in its infancy. Every telescope is a time machine, and this is only possible because light has a finite speed. That limit doesn't just restrict us. It grants us access to the history of the cosmos. It allows us to see the universe evolve. The most profound example of this is the cosmic microwave background, CMB. This is a faint, cold glow that permeates all of space. It is the remnant heat from the Big Bang, released when the universe was just 380,000 years old and cooled enough for atoms to form, allowing light to travel freely for the first time. This light has been traveling, stretched and cooled by the expanding universe for 13.8 billion years. When cosmologists study the CMB, they are literally collecting the oldest photons in existence, reading the blueprint of the infant cosmos. Light is the universe's historian, and it has been writing its story since the beginning. So here we are, gently floating back to where we began. We set out to answer a simple question: why does light have a speed limit? Along the way, we've wandered through fields of photons, danced with electromagnetic waves, and watched as time and space bent themselves around a single, constant number. The answer, in the end, is as elegant as it is profound. Light travels as it does because the universe is built for it to do so. The speed is not just fast. It is fundamental. It is a cosmic rule that holds everything together, from the interactions of atoms to the expansion of galaxies. It is the stitching in the fabric of space-time, the guardian of causality, and the messenger of history. It's woven into the screen you're looking at, the GPS that guides you, the starlight that inspires you, and the very biological rhythms of your body. You are a creature of light, living in a universe defined by its pace. Maybe we don't need it to be faster. Maybe in its unwavering, constant rhythm, it is already perfect. It gives us order, time, understanding, and beauty. It gives us stories and sunsets and the warmth of a distant star on a cold night. And so, as we bring this quiet journey to a close, let me ask you again. Where in the world are you listening from tonight? And what time is it for you? Wherever you are and whenever it is, thank you for spending this time with me. If this journey helped you wind down or sparked a quiet wonder, I'd be truly grateful if you gave it a like and tapped subscribe. It helps others find their way here to this calm little corner of curiosity. And if this kept you awake, well, at least you learned something wonderful while waiting for sleep to find you. Until next time, rest well, and may your dreams move at just the right speed.